In the higher quality video, I actually wrote these things out. Unfortunately, I didn't click the right button and get it here, so I'm not going to erase all this and rewrite it. This is very straightforward. Log 3 is 0.477 to 3 significant figures. Log 2 is 0.301 to 3 significant figures. Now, using all the significant figures I could get and calculating the quotient log 3 over log 2, I got 1.58. I'm not sure if dividing this into this gives you 1.58 or 1.59 or maybe even 1.57 or 1.60. It'll probably give you 1.58 or 1.59 because this number is actually very close. The next digit is 4 here, very close to halfway between 1.58 and 1.59. Well, then we see that our factor 3 curve represents the power function x to the 1.58, or at least is a very good approximation to the correct power. So now we plug in x equals 1/4, x equals 1/2, and I plugged in x equals 3/4. I didn't plug in x equals 2. I have to leave something for you to do. F of 1/4 turns out to be about 0.111. F of 1/2 equals 0.333. Now that's actually a good thing that this should be 3 times as big as this, because this curve is the factor 3 curve, and 1/2 is double 1/4. So in doubling the value of x, the value of y increased by a factor of 3, just as it should. Now 3/4 isn't the double of anything we have over here, and it kind of looks like we're getting a pattern, 111,333, but 634.634 doesn't fit that pattern. Okay, so if you didn't get that, you should run through that, make sure you understand it, and evaluate this for x equals 2 as well, and compare with the estimates you made here. Now, having obtained these 3 significant figure results, you can see how well you did in your estimates. Theoretically, this ought to be more accurate than this because this curve was carefully constructed and this was just estimated between 2 values of the factor. But that might or might not be the case. How well did you do? Was this an improvement over this? If so, why? If not, why not?